Hi all, welcome to a new video. Today we are going to discuss the energy band formation in solids. So let us begin. Before moving on to the solid structure, we have to consider the case of isolated atom. Okay. So we know that according to Bohr model, in any atom there is a central nucleus which is surrounded by revolving electrons, and the electrons are considered to be revolving around fixed orbits, isn't it? These electrons cannot occupy any energy level. Instead, they have to occupy certain permissible energy levels for them to stably rotate around the nucleus, and those permissible stable energy levels are actually visualized by these orbits. Okay, and these orbits are represented by the quantum number n, and we know that the number of electrons which can be occupied in each orbit is given as 2n square. So thereby we can calculate the number of electrons in each orbit, isn't it? But even though more than one electron is there in every orbit, no two electrons are having the same energy level. No two electrons in any atom can have an exactly same energy level. That is in accordance with the Pauli's exclusion principle. No two electrons can have the same energy level in any interacting system. So in an atom also, no two electrons are having the exactly same energy levels. This happens because even though there are more number of electrons in every orbit, their magnetic spin would be different, and that causes a difference between the magnetic moments, a difference in the magnetic moments between those electrons in the same orbit. Thereby each electron will be having a slightly different energy level in the same orbit. Okay, so thereby you are having discrete energy levels which are occupied by the electrons in an isolated atom. Now, what is happening in a solid formation? We bring together atoms of the same kind to form a solid. They are stacked together with very less interatomic spacing, isn't it? That forms a solid. So in a solid structure, the interatomic spacing will be very less, due to which there will be interaction between the neighboring atoms, especially the electrons of the outermost orbit. That is, the electrons which are revolving in the outermost orbit, they will have very strong influence from the neighboring atoms. That is, they will be attracted towards the neighboring atoms' nuclei, and also they will be repelled by the electrons of the neighboring atoms. In addition to their own attraction, the attraction from their own nuclei, there will be attraction from the neighboring nuclei as well, and there will be repulsion from the electrons of the other atoms. Okay, so this causes an alteration in the energy levels. In the isolated atom, they were occupying certain specified energy levels, and those energy levels will be slightly altered due to the interaction between the neighboring atoms. Since the atoms in the solid are all of the same kind, their electrons were also occupying the same respective levels when they were isolated, but now they have come together to form a solid. Now when considering solid as an interacting system, it is not possible to have the same energy level for any two electrons. That is in accordance with the Pauli's exclusion principle. So those energy levels are split to form new energy levels, which are actually separated by very small gap. Okay, they'll assume that you are bringing together n number of atoms to form a solid. Then for every electron of an isolated atom, that particular energy level is split into n levels in order to accommodate that particular electron from all the n atoms. Okay, so for every electron energy level, it is split into n levels if you are bringing together n number of atoms, and those gap between those energy levels are infinitesimally small. Thus you can assume that they are forming a continuous band instead of discrete levels. For every corresponding level there is n more replicas, and thus you can assume that you are forming a continuous band of energies instead of discrete levels. The energy band diagram of silicon crystal. As you can see, there are different bands of energy which are corresponding to the discrete energy levels of isolated atom of silicon. Okay, so in the case of silicon, the valence electrons are existing in the third shell. That is why valence band is shown as the third band. And here the valence band is shown to be completely filled. That is because when you form a solid, the silicon atoms are forming covalent bond with the neighboring 4 atoms. So they are already having 4 electrons in the outermost orbit, every single atom, and they will share 4 more electrons from the neighboring atoms surrounding. 4 neighboring atoms will share electrons, and thereby 4 covalent bonds are formed, and hence the outermost shell, which can accommodate a maximum of 8 electrons, become completely filled. That is why in the diagram the valence band or the third band corresponding to the valence orbit of silicon is shown to be completely filled. That means all the permissible energy levels corresponding to that particular orbit is already completely filled. So what happens? The electrons in that band, valence band, cannot move because all the permissible energy levels are already occupied. And higher up to the valence band, there is another set of energy levels which is represented as the conduction band. Conduction band means the higher orbits, higher than the third orbit. Okay, we are discussing about the silicon. So in the case of silicon, electrons are there only up to the third orbit, and higher up there are other orbits which are not occupied. The energy levels corresponding to those orbits are shown in the conduction band. Okay, so in the conduction band, normally in this diagram it is shown to be unoccupied. These are actually the next permissible energy levels which can be occupied if you supply some external energy to the electrons in the valence band. The valence band and the conduction band are separated by a particular energy gap known as the energy gap or band gap or the forbidden gap. Okay, so unless you supply an energy which is greater than the forbidden band gap, the electrons cannot move on to the higher orbits. When you supply an energy which is higher than the band gap, the electrons will be lifted from the valence band to the higher orbits or the conduction band. Okay, so in the conduction band, since all the permissible levels are not occupied, they can move. That is because the outermost orbits are having very less attraction from the nucleus. So they are almost like a free electron. That is why they are constituting to the flow of current. Okay, so the electrons in the conduction band are contributing to the conductivity of the material. So in the case of semiconductors, even at room temperature, the electrons are getting sufficient energy to exit from the valence band and move on to the conduction band. The temperature of the room temperature itself is sufficient for them to excite the electrons to the conduction band. That is why they are having a particular conductivity even at room temperature. That is why they are known as semiconductors. That is, their conductivity lies somewhat between insulators and metals, which are metals are very good conductors. Semiconductors lies just below the metals in the case of conductivity. Okay, the forbidden gap for silicon is almost 1.12 electron volt, and that of germanium is 0.72 electron volt. Okay, so that is the basics of energy band formation in solid. We have seen how the energy bands are formed, what is conduction band, what is valence band, and which band constitutes to the flow of free electrons in the solid. These are the basics. Okay, thank you.